In this video, we will derive a first formula for the advection equation, not only for the advection equation, but for any first order partial differential equation. We know that if we have, for example, some pipe or one-dimensional object, and this is x1 and this is x2. So if we measure a quantity q x t in this object x1 to x2 x1 to x2 dx, so we can measure it by integrating from x1 to x2. If I take a derivative of that, then it means that the quantity is changing inside this object in this geometry. And this is occurring due to the flux entering at point 1 minus flux which is exit from point 2. By following the same thing, we can also write the numerical version of this quantity. For example, we have d by dt x1 to x2 qxt dx is equal to f1t minus f2t. When we integrate this q, we put the value of x, and then the only variable is left is t. That's why we have t on the right hand side. If we write this as in the numerical method form, d by dt ci qxt dx is equal to flux at q x I minus 1/2 t minus flux at q xi plus 1/2 t, something like that. So what is happening, as we saw that we have this object and this problem was, or this equation represents this geometry. On the other hand, if we have, for example, some nodes, some geometry and some nodes, for example, this is I plus 1, this is I minus 1, and some intermediate value over here. So that will be I plus 1/2, and this is I minus 1/2. So this numerical scheme is acting like a geometry of this physical domain. Okay, so that's the equation of numerical method. If we integrate this equation by dt, for example, I integrate left hand side tn to tn plus 1 d by dt ci qxt dx dt. I am integrating from tn to tn plus 1 since I want to get the value in the time evolution. So the right hand side becomes tn to tn plus 1 flux q x I minus 1/2 t dt minus Tn to Tn plus 1 flux q xi plus 1 half T dt. On the left hand side, you can see that this dt and this dt will be cancelled out, and this d will be cancelled out from the integration. So what we get Ci, let me just write it neatly. We get Ci qxt dx evaluated at Tn. Since we integrated this, so we have to put the value of lower and upper limit. Tn plus 1 is equal to Tn plus 1 flux q xi minus 1 half T dt minus Tn plus 1 flux q xi plus 1 half T dt. Okay, so what we do, we put the upper limit. So we put the upper limit, that becomes Ci q x Tn plus 1 dx minus lower limit for the time t, qx Tn. This is left hand side, and on the right hand side we have Tn plus 1 f q xi minus 1 half T dt minus Tn plus 1 f q xi plus 1 half T dt. So we integrated this expression by dt, since t is continuous. So that's why we integrated with t. Now on the left hand side, you can see that we have a definition of Qn, but this definition is incomplete since there is delta x is missing. So we can write Ci qx Tn plus 1 dx. By definition, it was, if there is n plus 1, that will go into the power. It is not a power, but it just says that you are in n plus 1 level, and then we have I. So that is Qn plus 1 I. So the left hand side becomes Qn plus 1 I, but it only becomes Qn plus 1 I if we divide this by delta x. So we can divide it. We divide this by delta x, 1 by delta x everywhere. Okay, now it becomes Qn plus 1 I minus Qni, and the right hand side is 1 over delta x Tn to Tn plus 1 flux q xi minus 1 half T dt minus Tn plus 1 f qx I plus 1 half T dt. That's what we get. Now one thing we want to do over here is we want to put I plus 1 half first and I minus 1 half second. The reason is, whenever we want to measure something and take a difference, we always take a difference from higher values to lower value. Higher value is I plus 1 half, and the lower value is I minus 1/2. So we want to make this expression in the first term, and the first expression will go into the second one. So we can change that. So this will be equal to Qn. And one other thing we want to do over here is similar to what we have defined Qn plus 1, Qn plus 1i, we can also define Tn, Tn plus 1 flux dt, and we can take an average by 1 over delta t. That will be equal to F uh, Fn I minus 1/2 if there is Q xi minus 1/2 t, right? So this will be an approximation of the flux, but there should be delta t. So we divide delta t, multiply and divide by delta t. That's what we do. So we get Q n plus 1i is equal to Qni minus delta t by delta x, and then we have 1 over delta t, Tn to Tn plus 1 f q x I plus 1/2 t dt. Since we changed the value by taking negative as a common from here, and we also have minus. Let me just make some space. So that is equal to minus 1 over delta t, Tn to Tn plus 1, and there is flux at I minus 1/2 dt. Okay. So the right hand side, this becomes f n I plus 1/2. So we write it like this: Q n plus 1 I is equal to Q n I minus delta t by delta x. We have flux f n I plus 1/2 minus fn I minus 1/2, so on. This is our first numerical method. Generally, we assume that we have partial q by partial t, partial by partial x, and there is a flux which can be a function of q and t is equal to 0. So solving this problem, we have this thing. Let me just reiterate that we have one cell. For example, this is grid point. These are the grid points. This is I plus 1, I plus 2. This one is I plus 1/2. And this one is I minus 1/2. So what we are doing, we are calculating flux on the right boundary of the volume, and left boundary of the volume. So we are calculating Fi plus 1/2 over here and Fi minus 1/2 over here. We do the same for all the other cells. We calculate this over here, then we calculate, over here and over here, something like that. right? So this is our first numerical method. Now the only thing is left, how we can measure Fn I plus 1 half. Suppose we have these points I plus 1, I minus 1, and these are the dotted values. And over this volume, this is a volume. Over this volume, we calculated Qni. Over next volume, for example, this is the middle of two grid points. This is another cell, and that is Qni plus 1. So if we calculate flux over here, flux over I, I'm sorry, this is, yes, this is I plus 1 half. If we calculate flux at I plus 1 half at nth level, since there is no value exist over here, we can take advantage of the right value and the left value. It should be some combination of the right and the left value. Similarly, for this point, when we have Fn I minus 1 half, we can take advantage of Qn I minus 1. Okay, so that's what we have over here, Qn I minus 1. So at each cell, which is a boundary, at each cell we can calculate the value of flux from the neighbors. So in general, we write it like this. Qn plus 1, Qn plus 1 I is equal to Qni minus delta T by delta X. Fn I plus 1 half can be computed from the flux Qni, Qni, Qni plus 1. Similarly, for I minus 1 half, where is I minus 1 half? This is I minus 1 half. At this value, we can take advantage of Qni and Qni minus 1. So that will be equal to the flux Qni and Qni minus 1. That's it. Since we need a value of that over here. So that was our first complete formula of the first order PDE, partial differential equation. The only thing I want to discuss over here, such method like this is actually called a conservative form. It is a conservative form. Why it is called a conservative form? Since the interior values cancel out with each other, and the only contribution of flux or the change inside the geometry is coming from the edges. And we will talk about that maybe in next example. So what we do, we have a problem. For example, we just take a sum delta x, I is equal to capital I to j, Qn plus 1 I is equal to delta x, I is equal to I to j Qni minus delta T Fn I plus 1 half minus Fn j minus 1 half. What we did, we just multiplied this delta x with all the equations. After multiplying with all the equations like delta x, this is delta x and delta x, then we take a sum. When we take a sum, we will see that there is only one contribution which is coming from the edges, and we will talk about that now. Let me just go to an example. Our aim is to show that the fluxes are actually only depend on the edges. Suppose we have grid points. These are our grid points. According to finite volume method theory, we have middle point of these grid points. Suppose we have 1, this is 2, this is cell number 3, grid point number 3, 4 and 5. This one is called cell number 2. This is called cell number 3. This is called cell number 4. And you can see that the left cell is half and this one is half. As we saw that we have some fluxes, the contribution of flux is coming from capital I and capital J. Let me just put the value of capital I is equal to 2. It is starting from cell number 2 and ending at cell number 4. And the formula is Fn I plus 1 half minus Fn I minus 1 half. This is our formula. We just expand that formula. Remember that in this theory, the capital I is over cell number and J is where the cell ends. So we can write Fn 2 plus 1 by 2 minus Fn 2 minus 1 by 2 plus. Then we have Fn 3 plus 1 by 2 minus Fn 3 minus 1 by 2 plus. Then we have Fn 4 plus 1 by 2 minus Fn 4 minus 1 by 2. Okay. So we calculate 3 fluxes. This flux is computed in cell number 2. This is over cell number 2. This flux is computed at cell number 3. So this is over cell number 3. This is over cell number 4. This is cell number 4. So this is over cell number 4. Okay. So what we see if there is any cancellation or not. So let me just see that. For example, if I just solve that, that will be equal to 5 by 2 and this will be equal to 5 by 2. It means that this term will be cancelled out from this term, and then this becomes 3 plus 7 by 2. This becomes 7 by 2, and this becomes 7 by 2 as well. So these two terms will be cancelled out again. The only terms are left, these the terms are left from cell number 2, and the terms are left in cell number 4. It means the interior cell has been, the fluxes from the interior cell has been cancelled out. So we are only left with uh, fluxes from cell number 2 and cell number 4. So it means that something only enters from the left edge and the right edge, so on. So this is all about the conservation law. So it means that the quantity remains conserved. This method is conserved. Okay. So this was an example of flux cancellation. Thank you for watching.